All right, we just finished talking about crystalline structures and how they bond, but now we're going to look at bonding in metals instead, so solid metal. And we know that metals have specific identifiable properties, right? We know that they have high thermal and electrical conductivity, so they conduct heat and electricity very, very well. They are malleable, which means they can change their shape relatively easily, and they have a high level of ductility, which means that they can bend and they can take a lot of trauma basically without breaking. And these possibles are all, or these properties are all possible because of the non-directional bonds that are found in these metallic crystals. Metallic structures are special in that each atom is bonded to all other atoms surrounding it in all directions. And we imagine these atoms to be spheres bonded together in layers as closely as possible to one another. And each sphere is surrounded by other spheres at a tangent point. So there are six surrounding each of those spheres as well. And this arrangement is called closest packing. So it's as close as possible in all directions. And the layers fill out, so they're stacked in layers, and those layers fill in dimples in other layers that you will see on the next slide. And there are several different types of overlay as well. So you can see that, for example, in this top one, you have these six spheres next to each other, right, touching this one sphere in the center. And then those spheres kind of fill in those dimples so that this one will also be within that space for these other these other three spheres, and so on. So they continue on in this fashion, filling in spheres. So you can see that this first row is here, the second row fills in a space, and then the third, or not row, but the third column kind of fills in more spaces as well. So they're constantly being surrounded as closely as possible, right? Here's another way that they could be packed as well. And you can see that they have different layers, essentially, different ways, that they are packed. So you've got this little triad here that's packed into those spaces there. And so there are different ways of them packing as well. Down here, you've got another ability to where you have six almost set up kind of like dominoes, or not dominoes, but bowling pins would be, with another set of six combining to touch right on top of them, and they fit pretty nicely, and then those single spheres on the A's at either end as well. So that's what they kind of look like, and so metals couldn't take up any one of those forms, and bonding models need to be a few things in order to be successful. So first of all, they must account for the physical properties of metal, which we had just talked about, the malleability, the ductility, and the efficient and uniform conduction of heat and electricity in all directions. So when something warms up, like if you've ever cooked with a cast iron pan, you know that when the pan gets hot, the handle also gets hot as well, right? And that's the metal transitioning that thermal energy in all directions, not just in the lowest levels of the pan. So while the shapes of most pure metals can be changed easily, they're durable and have high melting points, meaning that bonding in metals is strong and non-directional, right? So you can hit a piece of metal oftentimes and it might dent or something like that, but it won't shatter like hitting a block of salt might. So we use this electron C model to kind of show that, right? So we have all these spherical metals that are bonded close to one another, and we don't attribute any electrons to a given metal, right? So we have a bunch of electrons that kind of float around, which is very helpful for the conduction of heat and electricity, okay? So because of those, the more atoms you have, the greater the energy required to break them apart becomes, actually. So if you have a larger piece of metal, it will become even more difficult to break apart. And these materials conduct electricity and heat very well because the valence shells of the individual atoms are actually only partially filled. They're not full to their full octet. And that allows for electrons to transfer very easily from one atom to another. And so that's kind of where we see that electron C field. And so the transferring of heat and electricity happens very easily as well. There's also a concept called metal alloys, which are basically you have the structures that lack filled valence shells. Other elements then can be easily put into those structures, so that if there's a space between structures, you can actually put another atom in there that you'll see here in a minute. And so the definition of an alloy is a substance that contains a mixture of elements and has metallic properties. And there are two types of them, right? So we have a substitutional alloy, which is one that some of the host metal atoms have been replaced by other metal atoms of a similar size. So brass, which is 2/3 copper and 1/3 zinc, is a good example. Other examples are sterling silver, pewter, and plumber's solder. An interstitial alloy is formed when some of the holes in the metal are actually occupied by small atoms. Steel is a great example of this, and that contains mostly iron, but carbon atoms fill the holes between the iron atoms. And this actually makes it stronger, it increases the boiling point, and it allows for a better usable material. Okay, so this right here is substitutional alloy, where you can see that some of those copper atoms have been replaced by zinc atoms, and that's in brass. And then you see in this interstitial alloy, you actually have little carbon atoms that are filling those holes between the spheres of iron. And those are really, really strong, even stronger than brass. And so you're filling those spaces, which means you're going to generally increase strength. The important thing here to know about alloys is that they still have very similar properties to that of other metals. In general, metal solid, so they won't shatter when you hit them, but they are less malleable, right? So it requires more force to make a dent in something that's steel versus something that's just pure iron, things like that. All right, that's all for this week, or for today, and I will see you next time.